Alright, good morning everybody. This is Mr. ARocena, and today we're going to go over electrostatic forces, because the other day we went over the basics of electrostatics. Today we'll talk more about how electrostatic forces operate. Alright. Alright, so to do this we'll first go over what Coulomb's law is, because Coulomb was one of a physicist who studied um, electrostatic forces a lot. And Coulomb's law basically describes the mathematical relationship between two charged particles and how they interact with each other. So this force can describe either an attraction or a repulsion, and it depends on whether you have a positive charge interacting with a negative charge, or a positive charge interacting with a positive charge, or a negative charge interacting with a negative charge. Regardless of what's happening, you can calculate the force as follows. Or the electrostatic force, so is equivalent to K times Q1, Q2 over R squared. So this Q1, this is charge of object 1, and Q2 is charge of object 2. This K here, this is, whoops, there we go. And this K here is called Coulomb's constant. Coulomb's constant. Oops, constant. And Coulomb's constant is much like the universal gravitational constant, just a constant that basically makes the equation work. This R here, much like with gravitational force, this is separation distance between the charges. So it's very similar to, actually, if you look at it very carefully, it's very, very similar to the law of universal gravitation, where law of universal gravitation was Gmm over R squared. Electrostatic force is KQQ over R squared. And so they're very, very similar. And they behave very, very similar to each other in that as our separation distance gets larger, the amount of force that the two objects feel gets smaller. And similarly, if things get closer, they feel more electrostatic force. Okay. Now, if F electric is less than 0, so basically if you have a negative electric force, then it is an attraction. Because that means you have a positive and a negative charge, so the sign of the force is negative. If your electric force happens to be greater than 0, then this is a repulsion. Okay. So there's kind of two conventions we have. So if we're discussing two different charged objects, if they're opposite in charge, they will fall under this this scenario where your total electric force is negative, so they will retract each other. But if they're either both positive or both negative, your electric force will end up being greater than 0. So then we call that a repulsion. That's what we observe. Okay. All right. All right. So that's Coulomb's law. This equation governs how we can determine the charge between two objects, or not the charge, the force between two charged objects. All right. Oh, and Coulomb's constant is this number here, 8.988 times 10 to the 9 Newton meter squared per Coulomb squared. And if you notice, Coulomb's constant is quite a bit larger than the universal gravitational constant, where Coulomb's constant is effectively 9 times 10 to the 9, and the gravitational constant was 6.67 times 10 negative 11. So this kind of gives you an idea of kind of how strong electrostatic forces are when compared to gravitational forces. Because since K is such a big number and G is such a small number, the electrostatic force can be quite a bit larger than gravitational forces, both for attracting and repelling objects. All right. now we have to define a new quantity, which we call the elementary charge, because we've never actually defined what charges were in previous classes. In Science 9, we first introduced the concept of electrons and protons, and we always said they have like an electron has a negative charge, the proton has a positive charge, but we never actually quantified it. We just always said it's +1 or -1, and we kind of kept this going up until now. So charges actually do have a unit, which is called the Coulomb. So this is a Coulomb. This is a unit of charge. And the charge that one electron or one proton has, we call that a unit of elementary charge. And we symbolize that with little e. Not to be confused with the mathematical little e, which is natural exponential, I think. Anyways, so the value of one elemental charge is 1.602 times 10 to the negative 19 coulombs. Okay, it's a very, very tiny amount. Very tiny amount. So the elementary charge is actually quite a tiny amount of charge. Okay, it's on the order of, that's Fermi. No, it's even smaller than that. Even smaller than that. I think it's a Fermi Coulomb. Anyways, but as long as you're dealing with just elementary charges, you can stick with the concept of one electron is one negative charge, so negative E, and proton is a positive electric charge, like that. And as long as you're dealing with just electrons and protons, that definition works out just fine. So here's an example. What is the charge on the object with 5 electrons and 3 protons? Well, 5 electrons is effectively negative 5e, and 3 protons is effectively positive 3p, so total charge here, total charge would be negative 5e plus 3e, so altogether we have a total charge of negative 2e, where e is the elementary charge. Okay. For those of you who took chem with me, or I guess Science 9 even, I always denote electron as an E minus, and part of that is because the E stands for elementary charge, and the electron has a negative elementary charge. The proton, my proton abbreviation was P positive, although honestly, if you're talking about just charges, you could denote the proton as an E positive instead. Although that's usually reserved for positrons, which are negative electrons. Yes, anti-electrons. We will discuss that later. All right. So yeah. So as long as you're discussing just protons and electrons, you can stick with this definition of total charge and just keep everything in terms of elementary charge. Okay. But if you're dealing with more than just small numbers of protons and electrons, like for example, if you're dealing with an actual electric current, then we have to define charge in terms of the Coulomb. Okay. Anyways, so the Coulomb, as a unit, we define the Coulomb as our unit of charge, and 1 Coulomb, we define this as the amount of charge that passes through a point in a conductor in 1 second if the current is 1 amp. Okay, so if we have a 1 amp current passing through a conductor, we can count the charge that it creates after 1 second, and that's 1 Coulomb. The other definition is that is the amount of charge possessed by 6.2422 times 10 to the 18 electrons and protons. Okay, that's a lot of electrons and protons. Okay. Now, most objects do actually have that many electrons and protons, but the difference, I guess, why most objects aren't charged is that we generally have equal amounts of electrons and protons. So, as a whole, most objects are very neutral. And if you do charge an object, most charged objects have charges in the microcoulomb range, so this would be 10 to the negative 6. So yeah, most charged objects have very small amounts of charge. Okay, because again, usually electrons will try to find their way to other sources of positive charge, and charges tend to even out relatively easily. It's hard to concentrate huge amounts of electrons or protons in a small area because of the laws of electrostatics, because they want to repel each other. So that's part of the reason why it's sometimes difficult to get really, really large charges. With that said, the next couple of examples are going to be really interesting. All right, so there you go. So that's the Coulomb. The Coulomb is our unit of charge, and 1 Coulomb is equivalent to this many electrons or protons. So it's 6 times 10 to the 18. Now, this has to be, if you want an object to have, so I'll make a note here. In order to have 1 Coulomb of charge, okay, you need an excess So you need an excess of 6.2422 times 10 to the 18 electrons or protons. All right, so you need a huge amount of charge for this. Huge amount of charge for this. Okay. All right, so let's go through some examples. Example 1. So here's what's the force exerted by a 1 Coulomb charge on or positive 1 Coulomb charge on a negative 1 Coulomb charge if they are half a meter apart. Okay, so this kind of gives you an idea of just how much force these two objects would have. So we'll take our equation. Force equals K Q1 Q2 over R squared. There's our equation. Let me just grab this and move it over. There we go. All right. So, using our equation here, K, let's just move my diagram over a bit. There we go. So K is 9, well, it's like 8.988 times 10 to the 9. We have a charge of positive 1 for Q1, charge of negative 1 for Q2. It doesn't actually matter which one you make Q1 or Q2. And then they're separated by a distance of 0.5 meters. This will be squared. All right. So calculating this out, pull up my calculator here, you get 8.988. Shoot, where is my? I don't see my exponent. This one. There we go. 9 times 1 times 1 divided by 0.5 squared. And you get a force in the order of 9 billion newtons. That's oh, whoops, that's not right. That should be I messed that up. That should be divided, not minus. Okay, let's try that again. So 8.9. Whoops. Okay. Does that mathematically work out? No, I'll just enter everything again. So 8.988 times 10 to the 9 times 1 times negative 1. Oops, 1 negative. Divided by, there we go, divided by 0.5 squared. There we go, that's better. So this has a force of negative 35 billion. Oh geez, 952, 123, 123. So negative 3.6 times 10 to the 10. Yeah, so about 36 billion newtons of force are going to be attracting these two objects together. Compare this to gravity, and I think, remember our example with gravity, we had two people attracted to each other over 2 meters, and they had such a tiny amount of force between them. Yeah, if you had two charged objects this close together, and they have huge amounts of charge, they will have huge amounts of forces acting on them. All right, On to the next example. Okay, example 2. There's another common example we see in a lot of physics books where we have a 3 spheres set up along or in a equilateral triangle as follows, and it asks us what is the net force on one of the charges. Okay, so they're all the same. So they're all positive half Coulomb charges. They're very, very close to each other, and we want to know what is the net force on one of these charges. Okay. All right. Oops. Wrong one. There we go. Oops. Okay. There you go. All right. So how we're going to work with this problem is you'll probably get another one like this in your assignment. So I would arrange them like this, as I've drawn here, with 2 sort of along a plane like this, and then this third one sort of up like that. And you'll see why I drew this sort of Cartesian plane-ish thing here. So what will end up happening is we'll call this Q1, Q3, and we'll call this Q2. So Q1 will exert a force on Q3. We'll call that force 1. Q2 will exert a force on Q3. We'll call that force 2. And we don't really care what Q1 and Q2 are doing to each other because it only asks us for the net force on one of the charges. And we're going to pick Q3 because it's easiest to work with Q3. You could work with Q2, but it'll require a lot more trig. All right, so as you can see here, F1 and F2 are both kind of pointed at an angle. They're not really straight. They're not straight on like in the previous example. But that's okay because we are told that this is an equilateral triangle. So this angle here is 60 degrees. So that angle there is also 60 degrees because this is an equilateral triangle. So this actually works out really well because if you remember from our vectors unit, if I have forces at an angle, I can always break that force down into 2 component vectors. So I will have a component vector this way from that force. F2 will have a component vector this way. And then we have component vectors going up and another component vector going up like that. Okay, after I've drawn these arrows in, it should be hopefully clear where we go from here. The x component of F1, so we'll call that F1x, and the x component of F2, we'll call that F2x, they're going to be, because all the numbers are the same, so the distances are the same, so this distance is the same as this distance, the charges are both half Coulomb positive charges, so F1 and F2 have this exact same magnitude, which means F1x and F2x have the exact same magnitude. The only difference is that the F1x and F2x are going in opposite directions, so they will effectively cancel out. So the only things we really have to worry about to find the net force on charge 3 is what are the y components of F1 and what are the y components of F2. And for that, we need to know what is the actual F1. Well, F1 is going to be K Q1 Q3 over R squared. So this will be 8.988 times 10 to the 9 times a half Coulomb positive charge times another half Coulomb positive charge divided by 0.2 squared. All right, so let's calculate this out. So 8.988 times 10 to the 9 times 0.5 times 0.5 divided by 0.2 squared equals. So this F1 will have a force of 56 billion newtons. 5.6 175 times 10 to the 10 newtons. Okay, so that's F1. But we don't actually want F1, we want the y component of F1. Well, let's figure that out. Based on my triangle, So there's my triangle for F. There's my hypotenuse for F1. This is what we want. We want the F1y component. There's 60 degrees. So F1y will be the sine component. So this will be F1 times sine 60. Okay. So I'll take our answer. We'll multiply this by sine 60. And we get an answer of not as big. It's about 449 billion. So 4.86. 4.86 times 10 to the 10 newtons going up, or I guess north. And F2y will also equal 4.86 times 10 to the 10 newtons because of symmetry. Remember, F1 and F2 are the same. Their x components are just in opposite directions. So total net force on Q3. So net force on Q3 will just be those two added together. So that'll be about 9.72 times 10 to the 10 newtons going north or up. We'll just say north for simplicity's sake, going north. There you go. So you can treat these electrostatic forces in the same way as you do any other force vector. Okay? So in a problem like this. Now, like I said, you could do the same thing with Q1 and Q2, and you'll get the exact same result. It's just the direction will be slightly different. So if I were to do Q2's force would be in this, something like this. And Q1's force would be going in this direction. The magnitudes of these two forces would be the same as this one. So the magnitude of the force on Q1 and Q2 will be the same as this, but it just requires a lot more. I mean, not a lot more, just more trig to figure out the exact direction it's going in. All right. Okay, on to the next example. Alright, so here we are given the force of repulsion instead on two identically charged spheres, 4 newtons when they are 0.25 meters apart, and it asks you what is the amount of charge on each sphere. Now the important thing here is that they are identically charged, otherwise this problem becomes really difficult. So they are identically charged. Well, I should say it becomes difficult, it becomes impossible, because you can have so many different ways to get this if they aren't identically charged. So anyways, so yeah, if each charge has the same amount of, or each sphere has the same amount of charge, we can basically just call them both Q. And when you write our equation, we get the following. F equals K Q Q over R squared. QQ. Don't QQ over this problem. All right, so this ends up simplifying as follows. All right, so now when we solve it, we'll get the following. We'll put in some numbers. So force was 4.00 newtons. Coulomb's constant, not gravitational constant. Q squared, all divided by, they are separated by 0.25 squared, and we get the following. Rearrange this, so we have 4.00 newtons times 0.25 meters squared divided by 8.988 times 10 to the 9, and then we square root all that to get Q. All right, there's my calculator. I'm going to do this on this calculator. We square root first? No. Okay, so I go 4 times 0.25 squared divided by 8.988 exponent 9. Okay, and then we'll square root that. And we get a charge of ridiculously small 5.87 times 10 to the negative 16. So Q is 5.87 times 10 to the negative 16 coulombs. Q. Then as an extension to this, if you felt like it, you could figure out just how many excess protons this object has. Although it's not really excess protons, it's more of a deficiency of electrons, because electrons, stripping electrons is a lot easier than stripping or adding extra protons to things. Nice, there you go. So that would be the amount of charge present on both spheres that would allow them to feel a force of 4 newtons between them if they were a quarter of a meter apart. All right, last example. So here we have 2 charged 1 kilogram spheres. They're going to be placed half a meter apart. They repel each other and they travel with an initial acceleration of 1.0 meters per second squared to the left and right respectively. Why is there an acceleration? Because I felt like giving you guys a slightly harder problem. Actually, it's not really that hard at all, because if you have an acceleration and you're dealing with forces, this is probably going to at some point boil down to Newton's second law, which is force equal, or F net. I should make this explicit. F net equals mass times acceleration. So all we need to do is figure out what is the net force acting on each of these spheres. Okay. Do I mention it here? No, I do not, but let's make it explicit that these have the same charge. So they have the same charge. Okay. And it basically becomes the same thing as the last example, where we have to calculate the force on each of the chart or on each of the spheres. And then once you have the force on each of the spheres, you can calculate the net force. So let's work this out. All right, so at some point we need to figure out what the net force is on these spheres. So let's focus on the one. Since they're charged identically, we don't need to worry about the other one, because we can just say, okay, F equals K Q1. I guess it's the same, so I can just skip this and go straight to KQ squared over R squared. Okay. If I wanted to be really I guess, skip a few steps, I can just immediately put in, why did I do that? I can immediately put that in, and then I can change that to mass times acceleration equals K Q squared over R squared, like that. There we go. Okay. I have a mass. Each sphere was 1 kilogram. They were accelerating at 1.0 meters per second squared. I'm glad I chose easy numbers. Coulomb's constant, 8.988 times 10 to the 9. Q, we don't know what Q is because we're asked to find it. And they are separated by half a meter. There we go. All right, doing some algebra, we get the following. 0.5 squared times 1 times 1 divided by 8.988 times 10 to the 9. That's Q squared. And then we just square root everything. And that'll get me Q. All right, calculator time. Okay, so 0.5 times 0.5 times 1 doesn't matter. Divided, no, that's a minus. We want to divide. There we go. Divided by 8.988 times 10 to the 9, and then we square root that, and we get another small charge, 5.9. Yeah, 5.9. That's the same as the other one. 5.9 times 10 to the negative 16, and that'll be in coulombs. Right? Yeah. There we go. There. All right. So yeah, so the amount of charge necessary to do certain things is usually actually quite small. They're never that large. Like anytime you have, if you ever get like charges in the Coulomb range, that's a lot of charge and can do a lot of messed up things because they will attract they will attract things to them with huge amounts of force. Yeah. So in most cases, again, most charge objects have charges like in this range or nothing really greater than micro Coulomb range. Okay. All right. If you guys have any questions, you can come find me tomorrow or ask me through other ways to how to contact me. Your assignment for the rest of the day then is there, and tomorrow we will work on some lab stuff. All right. I will see everybody later.